Okay, so continuing with our morning program, our next speaker, our second speaker of the morning, and welcome again to the online people. Our next speaker of the morning is Jeff Carlson.
Thank you. All right, so all of this is joint with Chen He, and it's called Equivariant formality of co-rank 1 isotropy actions and products of rational homotopy spheres. I guess I'll write that out. Okay, so. Co-rank 1 isotropy actions, and then that's too long, so we're done. All right. So the overall topic is a question of when a certain action is equivariantly formal, and so equivariant formality of an action of a group on a space is surjectivity when it happens of the restriction map from Borel equivariant cohomology. Is the quotient of this sort of fattened up object by a diagonal action of the group. Just the restriction to the cohomology of the space itself. And yeah, I think this is still visible, right? Okay, this is above the visibility line for this board. All right. Can't do much more than that. All right, and so this was defined by Borel in 1960, but not as such, just as an example of a condition. So this goes back to Borel in 60 rather. And then Gresky, Kotwitz, and McPherson formalized this, defined this formally in a paper that I think it came out 97, 98. Yeah. Knew someone here would know this. All right, and so the examples, the famous example, which is probably this audience knows, is what's called a GKM manifold. You can think of as, let's say, this is one definition. There are a number of competing definitions. An almost complex manifold M with torus action, isolated fixed points, and weights of isotropy representations, so of representations at fixed points. Pairwise linearly independent. Okay, so suppose you've either already countered that or that's not convincing. But so one famous example, I want red, for example, is if G is a compact connected Lie group, which it always is, and T is a maximal torus, and one example of this is the left action of T on the right quotient GT. So is equivariantly formal. All right, and let's see, so general question you could ask is what happens if you use some other group, subgroup of G in this? So you could ask about other groups. It turns out that G, the same action of the translation action of G is also equivariantly formal. But if I pick some other subgroup K of G and say that K does not contain a maximal chorus, then the action of T on G mod K, for example, is not equivariantly formal. And so in particular, on the other hand, if you get all the way down to a point or something, then it's equivariantly formal again, just because there's the action isn't doing anything. So there's a question of at what point your group gets small enough that there's this question. So the first interesting question really is for K is small enough that this might be equivariantly formal. When is this equivariantly formal? That's sort of the general question that this is about. So that we don't know. We know in subcases. All right. Yes. What? That's a good question. I will always use rational coefficients now. Yeah, so I should put that in the definition here. Yeah, these will be rational coefficients always for us. Thank you. Yes. All right. Okay, so K and K from now on is connected compactly group as well. Right, and so we know some cases, yeah, so we have a few reductions in some cases where we know this is the case. And I should say, I'll lead with just the things we know. So known. So one case is when K, actually, I'll give the reduction first. So reduction. And this is me, I guess, from long ago. It's that this action is equivariantly formal if and only if the restricted action of the maximal torus is also equivariantly formal. So somehow this really depends only on the maximal torus of this smaller group, not the entire group. Somehow this is in some weird way, this is a property just of tori. And this enables some other examples from what we know. So yes. Yes. Potentially, yeah. I tend to assume G is compact to begin with, but yeah, in theory you could do that. Yeah, why not? Yeah, you can do this for anything. It turns out that there's also reduction from non-compact to compact near the beginning. You can look at the max. Yes, yeah. Yeah, that's absolutely fine. Yeah, this is yeah, this setup here is completely general. So then one example comes from what I just said. It's if H or let's say K and G is of full rank, which means it contains a maximal torus. We always named ours because then you can use this twice. You can use the fact that you know that this is equivariantly formal, and you can use this to transition. So that's one class of examples that was known. This is due to Chica. If the cohomology of G surjects onto the cohomology of K, which comes something like K being a factor of G, not exactly surjective, then it's known. This is Oliver Gerches and Sam Nashari. It's if K is the identity component of some finite order automorphism of your Lie group. So this is a generalization of G mod K being a symmetric space. G. This does not go up. Okay. And then 4, I guess this is me again, is for the low rank case, I thought this would be at least easy to study if K is very simple. So yes, if K is isomorphic to SU2 or SO3, and then on the other hand, if K is a circle, then yes, if, and these are exclusive, there's this surjectivity. So He to HU1 surjective. Or, and then whatever this U1 is, if it's somehow flipped by an element of G, so I'd say it's reflected. So if there is G in G such that Z goes to GZ, G inverse is the same as inversion on your circle. So that's sort of, yeah, that's this summary of general things that you do about this. And for this edition, the question was, I know what happens if K is of rank 1. What happens if K is, I know what happens if K is of full rank. So the next question is what happens if K is of rank rank of G minus 1. So 5 topic. And the surprise is that this turns into a classification of something that's fairly well known, where some group related to K, we'll call it H, is such that G mod H is rationally homotopy equivalent to a product of 2 spheres. So this, yeah, I didn't expect. And so I'll list some lemmas and I'll say how this goes. There's basically a reduction that simplifies your pair of groups substantially until you get to a table where these things were mostly classified. And we finished it, basically. So, yes, yeah.
What are you using to recognize formality
So
in these calculations? Thanks.
So I recognize formality by calculating the differentials in the model and looking for a regular sequence. In this particular example, what's going to wind up happening is a lot of these things are going to be rationally equivalent to either one odd dimensional sphere or the product of an odd and even dimensional sphere. And then those models you just look at and you happen to already know those are formal. So evaluating things for formality doesn't come up so much in this because we have like a ideal simple example that's closely related. Okay, so I'm just going to list, I'm going to say what goes into this sort of like morally why anything might work and then get to the reduction, I guess. So, yeah, so here's one theorem that I think is what Tony was gesturing at. This is due to me, fuck. And so that this is, I'm going to, let's introduce notation as well. I will say that the pair G mod K is isotropy formal, even though it's a terrible term that probably shouldn't be propagated, just because it's easier than saying K acts on G mod K equivariantly formally. Okay. Right. And so one of these is that a pair G mod K is equivariantly is isotropy formal, since I wrote this now. If so there are two statements of it. One is that, and S is always the maximal torus of K, remember. One is if the normalizer in G of S modulo the centralizer of G in S. So these are the elements that act on conjugation by G on S in some way. So this acts on the Lie algebra of S as a reflection group. So it's generated by reflections through hyperplanes. And this reflected circle is like is the first example of that. And restriction map from cohomology of the classifying space of G to invariance of the classifying space of N under this action is surjective. So that's one. And or equivalently. This surjectivity statement again. And G mod S or G mod K equivalently is formal in the sense of rational homotopy theory, which I think accounts for Tony's question. So the name equivariant formality was chosen out of like resemblance to formality and nothing particularly stronger. It happens to be in this case, however, that there is overlap with actual formality. You do need your space that it's being acted on to be formal. I wander over here. Okay, and yeah, so what we wind up with is basically an algorithm that decides this in case of a given pair. It's a bit like a classification, but not all the way there. Okay. Oh yeah, so I'll give one more theorem. This is I'd say Shiga Takahashi have a version of this, and Oliver and Samashari also have a version of it. And I have a different version of it that I find more useful, but it's all basically the same thing. So the theorem is that the dimension over Q, so as a rational vector space of the cohomology ring of this homogeneous space is at least 2 to the rank of G minus rank of K times the order of this is a coset. So effective quotient of the normalizer of S in G versus effective quotient of the normalizer of S in K. So it's really, you can think of both of these as in the automorphism group of this Lie algebra. And then these wind up being both finite groups. And yeah, so there's this inequality with equality just if and only if the pair has this equivariant formality property. So this reduces things to a counting problem, assuming you can compute cohomology, I suppose. And so corollaries. So one is if your the cohomology of your space is the same as that of a sphere of, I said of odd dimension in this case because that's more relevant to us, then and that's because in that case this is 2 and this is 2 and this is forced to be 1, so those are equal. And then if this happens to look like a product of 2 spheres cohomologically, which will turn out always to be 1 odd, 1 even dimensional, then you have this isotropy formality if and only if this number winds up being 2. As rings, but really vector spaces will be enough in this situation by Poincare duality. You really just need to count that there are 4 generators and degrees. Yeah. Yeah, so then, yes, this is isotropy formal if and only if the size of this group, which I'm going to call N, is bigger than the size of this group, which is the Weyl group of K. Because it will contain it, and if it's strictly bigger, it will be twice that, and that's all that can happen. All right, and so because this is so simple, it would be nice if there was some way of replacing K with some group that gives this, and that's basically what winds up happening. So that was the first surprise. That yeah, so just I'm recalling here's G, here's a subgroup K, here's a maximal torus. So groups, tori, and then Lie algebras. I'm going to name Fraktur T and Fraktur S. And you can use the killing form to look for complement to S, which we're assuming is one-dimensional in this case. We're assuming the ranks are one different. So T is the sum of S and some perpendicular that is one-dimensional. Great. And what we do is we just define out of nowhere. It's not out of nowhere. We find Onishik has considered this too. So we consider this group that is the commutator of the centralizer in G of this orthogonal complement generated by this and S itself. And this is going to contain G. It's going to be connected and closed, and it's going to have HS contained in centralizer of this, and it's going to be the biggest possible group that does this. So maximal closed, connected with this property and with S as a maximal torus. And this should be contained in G. I don't know what. Yes. So it's this commutator of these two centralizers or stabilizers and just S. And it's just this. It is a larger group. It is a maximal closed connected group containing this S as a maximal torus, I believe. And yeah, so this is going to be our replacement for K. And it turns out that this works out very nicely for us. So it winds up where the normalizer of this S is going to contain the Weyl group of this HS, and with the strict containment, if and only if, let's do a picture here. So here's a picture of T, here's the Lie algebra of S, here's the one-dimensional complement within T, and there's a question of whether there's a group element that stabilizes S and flips this RV, is what this question winds up being. So this winds up being the same as the longest length element in the Lie group, in the Weyl group of G, preserves S and flips this other guy. And I guess the other thing that you need is that, but W there's no element of the Weil group of H of S that does this. So this is a distinct element. Okay, so there's this kind of unlikely reduction, but this always exists. Then you examine this group, and then this group is very likely to be such that the quotient is rationally a product of two spheres. Okay, so now there's a statement of the algorithm, basically. And, no. So algorithm. Step one is place G, the original pair, where S is its maximal torus, with G of HS. And we have this lemma that I think I haven't erased yet, that says that the answer will be the same for this question. So our placement question 2, it's determine whether or not this has the quotient has infinite fundamental group. If so, not exactly, but up to a covering, you have a sort of decomposition. If so, I'll say basically, cover myself, the pair G mod HS is some pair G prime HS and an extra S1 factor, and that's enough to give equivariant formality. And so if not, continue. So I'll set D to be the dimension of this cohomology ring as a vector space. So if this is 2, this thing looks cohomologically like a sphere, and the pair is isotropy formal. If D is 6 or more, it's going to be even. Then it's not so. And then if D equals 4, then it's going to be, and I said this aloud above, but it's going to be the case that the cohomology of your quotient looks like that of the product of two spheres. Right, and we perform a further transformation. We map both of these. So HS is contained in G, and there's a map given by left translation from G to the homeomorphisms of this quotient space. Right, it's some transitive action. So you can map both of these in there and consider their images. This is to reduce things to something like a classification problem. We're looking for like known homeomorphism groups, and then this reduces the number of possibilities for what this image is going to be. So consider the images called G bar and H bar. All right. And you move forward. So 4 is consult the table. I can say a bit more about how the table is constructed. If G mod H is not on the table, the original pair is not isotropy formal, then if it is on the table, see whether this is, there are some general patterns for how to check, but overall it's sort of, there's nothing that works like for every pair. You just sort of have to check one by one for in terms of the dimensionality and these normalizer conditions. If it is on the table, see whether the table says yes or no, because I included that in the table. And so I'm going to ask for the table now. I think Shushin was meant to come, create the table. And then I'll talk about the table while I wait for him to come. It's just going to come and it will display on the screen. And
Could you just repeat the
Yes.
assumptions on G? The assumptions on G.
Yeah, so G starts off life as a closed connected, a compact connected Lie group in this talk.
And what about its formality property?
So it itself is formally, I guess, because its cohomology is an exterior algebra. I'm not assuming anything about the formality of G mod K or G mod S. And of course, by the other theorem, it will wind up being formal if the action of K on G mod K is equivariant formal. Have we contacted Shushin?
Yeah.
All
Yeah,
right.
sure, that would be okay. He should be
okay.
in his office there.
And I'll say something about the provenance of the table, I guess, and then I'm done. Because there were existing classifications that did almost what we wanted, but not exactly. And there were some cases left out and some cases wrongly added in some. So I'll just say, so the table is partially us. In Shenhe. Large part is Kammerich, a Dutch guy, did a PhD thesis around 1980, determined when G mod H is actually homeomorphic to sphere cross sphere. And let's see, and then Linus Kramer and his students, then Kramer's habilitation thesis tried to classify these things with the right rational cohomology. And did more or less. And then he had two students, Wolfram and Let's Siebert, who covered a few remaining cases in their theses. Okay, and this is just warming up, I guess. And I share maybe.
Do you see it? Do you see it on your computer?
I see it on my computer. I have to go to Zoom and ask to share again, I think. Oh. System window capture, maybe. Let's try this. Table rotated, sounds good.
Usually this is a formality.
Yeah. Anyway, so yeah, here's the table. And So relevant things in the table turn out to be if there's any larger transitive subgroup acting. That's a question about the centralizer. If you have a larger subgroup acting transitively, then it will need to commute with the other groups. So looking for the center is relevant. Yeah, and then some other things you can rule out. Sometimes you can rule out something being isotropy formal by existence of a larger group. Anyway, this is page 1 of the table. And once you've absorbed, there will also be page 2 of the table.
Shouldn't that 14th subscript from the right be a 1 instead of a 2?
Let's see, we're from the right on which row, honey?
No, it's just,
Yeah, I know.
it's hard to see. It's hard to see.
I know it was going to be worse up there, or maybe it still is. Right. And then, yeah, okay, here we go. Here's page 2. And that's, yeah, that's the table. What to say about this? Yes, a lot of these were already given to us, but some of them were only checked for sufficiency, and then you had, if they satisfied some sufficient condition, then you had to check whether they actually, the quotients actually had the right cohomology and things like that. Or sometimes look for something in a normalizer or the absence of something in a normalizer that did that reflection trick. And yeah, this is just a lot of case-by-case computation.
Which was the hardest to prove?
Interesting. I think some of the ones with F4 involved learning interesting things about the octonionic projective plane, I think, if I'm remembering properly. And then one of the ones that wasn't the hardest per se, but tripped me up for a bit was one that was included in an earlier version of this table that I was going to try to find on this table, but it isn't here because it's not actually. But no, I think this is actually the G3 of R6 over there. I think tripped me up for a while because it's a non-example, and we were told it was an example initially.